Okay, now that we're comfortable with the XY coordinate system and looking at points plotted on the XY coordinate system, now we're going to move on and we're going to look at graphing linear equations on the XY coordinate system. So I want to look at some of this verbiage I have down here in my notes. Any equation with two different variables and no exponents is a linear equation. So I want to focus on what we mean by a linear equation and what is not a linear equation. So I've got some examples here that I just kind of whipped up. These first four are all examples of linear equations. You've got, two different variables. In each case I used x and y just because we're going to be plotting on the XY coordinate system. They're in different orders, different scenarios going on with the algebra. In fact, in this one here, we have, two different y terms and two different x terms. But from the work that we did with single variable equations, we learned how to collect like terms, which we could do that here, collect like terms and continue on simplifying. So all of these first four are linear equations. You could plot them and you'd come up with some kind of a straight line, although that does not look like a straight line. You would come up with some kind of a straight line. These last two have a variable. In this first one, we've got y has a variable or has a power of 2. And the second one, our x variable, has a power of 2. So we have two different exponents here. It wouldn't matter if that exponent was 10 or 7 or whatever. An exponent is an exponent. And so those would not they would not be linear equations. They would create some kind of a curve, perhaps like that or perhaps like that, but it would not be a straight line. So we are not going to be talking about these. We are talking about equations where you've got two different variables, maybe several terms with the same variable, but we're going to be looking at linear equations. And actually this first one is the one that I'm really going to zero in on a lot, where you have y over on the left side by itself, followed by equal to an x variable term and then a constant term. That's called our slope-intercept form. That's golden because we get a lot of information off that one. So that's the next thing that we're going to go into, talking about the linear equation in the form y equals mx plus b. That's just a general format, is in the slope-intercept form. And we're going to talk about both of those terms, where m is the slope, and b is the y-intercept. So we're going to talk about what all of those things mean. Okay, the xy in the y, in fact, I'm going to write this up here again, y equals mx plus b. All the pairs of xy's that create that true statement are points that fall on that equation. Okay, so we're going to start out looking at the formula for slope, which is rise or fall, which is change in y, and I should write y1 and y2 here, x1 and x2, so you recognize those are different points there. The rise and fall, the change in y. Rise or fall is change in y. And then the run is the change in x. That's your horizontal difference. And so I'm going to look at these 2 points here, the star points, and then we're also going to look at the dots here, and we're going to look at these as points on a line. In fact, I probably could connect those, but before I get doctoring up this diagram, I want to go ahead and let's just review practicing identifying these points. This first point here, this first star, has an x-coordinate of 2 and a y-coordinate of 5. So that would be 2, 5. And this next point, star, would be 4, 8. X-coordinate is 4, y-coordinate is 8. If I want to, I should really go ahead and connect these because that's the whole point of this lesson, is connecting and creating linear equations. So we're going to look at this one, and so we can see that there's kind of a slant to that. And we're going to talk about that slant as slope, and we're going to calculate that slope. Now the second set of points here, I have the first point, I have a coordinate of 4, and the second coordinate is also 4. So that point is 4, 4. The second point here is, I'm counting over 9 along the x-axis, and the y-axis is 1. If I want to, I can go ahead and connect those and see what that line looks like. Okay. So now we've got a picture of two different lines on the same coordinate system. That's probably nasty. I probably shouldn't do that to you, but I want to talk about two different examples at the same time here. So this first point here, this first starred line that's going up as we look at it from left to right, I'm going to look at the change in the y-coordinate. My y-coordinates are 5 and 8. We can see that the first coordinate, the y goes from 5. The second coordinate, the y-coordinate is 8, so it went up 3 units. Whereas over here, when I look at the change in the x-coordinates, I've got 2 to 4 here. So the change from x to x, from one point to the other, one coordinate to the other, I went from 4 to 8, and so there's a change of 2 there. So we went from left to right. So that's just a pattern there, and I want to look at what happens here when we plug in the formula, looking at the difference in y-coordinates and the difference in x-coordinates. First of all, I'm going to write down these points. Over here I have 4, 8, and we had 2, 5. Actually, I wrote these in a different order, but a lot of times students like to connect the x's and connect the y's, or they go ahead and they try to plug in whatever point you start with for your y-coordinate. Let's say I start with a y-coordinate of 8 here for my first point minus my second point. So that's going to go in the numerator. So 8 minus 5. In the denominator, my x-coordinate for the first point is 4 minus the x-coordinate for the second is 2. That 8 minus 3, or I'm sorry, 8 minus 5 is 3. That 4 minus 2 is 2. So we can see that we've got a slope. We've got a slope here of 3/2. So that's the slope of our first line. Now notice we've got 3 and 2 here when we plotted out the changes here. So think about this. When you go from this point to the second star point, I've gone up 3 and over 2, which means this was my rise. I had a rise of 3 and I had a run of 2. And that's all communicated with this ratio of 3 over 2, which communicates the change in y over the change in x. That's that ratio. So I'm going to look at the second line here. I've got points 4, 4 and 9, 1, but I'm going to do this one a little bit differently. A lot of times students like this method, 4, 4, where I stack the points, I should say, over 9, 1. Just gets a little loopy here with all the parentheses. But they ask themselves, how did I get from 4 to 9 to figure out that change? How did we get from 4 to 9? Looks like we added 5. And what did we do to get from 4 to 1? That's a little different motion there. We subtracted 3. Now keep in mind, this is all your x coordinates. This is the change in x coordinate from an x coordinate of 4 to an x coordinate of 9. In my slope, that goes in the denominator. The change in x goes in the denominator. So the slope in the second problem is going to have a change of 5 in the denominator because that's the change in x. Even though seems like we're calculating this a little bit out of order. Now the second change here that we calculated was our change in y, our y coordinates. We went from 4 down to 1, and that was a change of -3. So we have -3 here. So this slope would be -3/5 for our second line. Now let's take a look at this. When I look at my change in x, I went from 4 to 9 here. There's a change of 5 here in my denominator, in my change in x. But when I look at my change in y, if I do that, I guess I'll do that over here. I went from 4 down to 1. So I have a change in 3 units here. So you can graphically see that here. Or you can just algebraically. We wouldn't have even had to plot all this. We could just be getting our 2 points and calculating, which is what we're going to be doing next. Okay, so we've got two different examples here that we're going to work with. We need to find the slope of the line containing these 2 points. So this one, I'm going to do the first one where I connect my x's and connect my y's just to kind of make sure I grab the correct ones. I always tell students just, draw your fraction line. And I don't know about you guys, but I always like to, it's just my eye wants to grab that first number there. Well, I have to remember that first coordinate is an x coordinate. My change in my x goes down in the bottom. So I'm kind of building my fraction from the bottom up. But my first coordinate is -2, and I'm going to be subtracting 3. But if I start with that point, I have to for x, I have to start with that point for y as well. So I have -1 minus 1. And that's going to give me a slope of -1. Collective -1 is -2. -2 and -3 gives me -5. Well, I need to recognize that a negative over a negative, there's a pair of negatives, that's going to make that a slope of 2/5. So you're like, great, big deal. So I know between these 2 points we've got a slope of 2/5. Let's go ahead and plot these points and get an idea what that looks like. So my first point, again, we're going to plot is -2, -1. If you remember, you're starting at the origin. I'm counting back 2 and down 1. So there's my first point. Second point is over 3 up 1. So I'm starting at the origin, go over 3 up 1. Okay, so again, grab my little card here, and I'm going to draw a connection here between these two. So what I found is that I have a line that looks like this. And I can see that from this point to that point, I had to count up 2 and over 5 to get to the other point. What this tells me is that any point on this line, I could start with a point way over here. If I count up 2 and over 5, I'm going to land on the line. If I count a point from here, up 2 over 5, I would land on the line again. So that change is constant. That's what makes this a linear equation, a straight line, that no matter where I grab a point on this line, I should be able to count up 2 and over 5 and land on this line again. Okay, let's go ahead and practice the second one here, where I'm going to do the other method where I'm going to stack my points. And I'm not going to put my parentheses or my commas in here. I'm going to have 2, actually maybe I'll do it like that. -2, 4, 3, 0. And I'm going to ask myself how to get from there to there. How to get from -2 to 3. Looks like I added 5. And how did I get from 4 to 0? It looks like I subtracted 4. But keep in mind that this is your change in x, so that goes down in the denominator, so that's 5. And this is my change in y, so that goes up here. So this is saying that I have a slope of -4/5. So let's go back and plot these points and see what that looks like. So we have -2, starting from the origin. I count back -2 for this first point, and then I'm going to count up 4. Okay, for the second point, I'm going to start at the origin. I'm going to go over 3 and up or down 0. So there's my second point. And I'm going to draw the line that connect those with a line. And I can see that this line falls going left to right. And again, the same thing holds true. If I would find a point over here, that I would count down 4 and over 5, down over 4 and over 5, down over 4 and over 5. I would keep landing on that point, or on that line. No matter where, I could pick a point anywhere. If I counted down 4 units and over 5, I would land on that line. So this is a constant rate of change from one point to another point and landing on the line. Okay, so one of the things that I want you to see is that this first example, we have a positive slope. And you can see when you're looking at this line going left to right, it rises. So I want you to recognize that positive slopes, it rises going left to right. Whereas this next one, we have a negative slope and it falls going left to right. So a negative slope would look kind of like this, where it would fall. So I'm going to use the word fall in here, and rises. Some other words that we think of when we look at this is that as you go left to right, do you see how your x-coordinate automatically increases, going from -2 to 3, the x-coordinate increased. So did my y-coordinate increase. And this is called an increasing function, and an increasing rate of change. Whereas this one over here, my x-coordinate was -2, And when I went over here to 3, again, going left to right, my x-coordinate's going to rise. But here my y-coordinate fell. And so this is called a decreasing function or relationship. Okay. Another term that we put to this is, a lot of times when you're putting data, you're plotting data, and your data is going to fall in this first quadrant here. And you'll notice if things are rising, you'll say that you have a positive correlation. In other words, as one variable is increasing, the other variable is increasing. And that's very standard on that positive or increasing function there. And this one here, a lot of times if you're plotting data in this upper quadrant, and you'll notice that your information is decreasing as you go from left to right. That is called a negative correlation. So that really drives right off that term of negative slope, negative correlation. I think this would be a good point to stop this. We'll continue looking a little more at this.